start doing. Okay, thank you, Tomoyuki, for waking up so early and willing to give us the seminar today. Today we are happy to have Tomoyuki Arakawa from Kyoto University, who's going to tell us about 4D-2D duality and representation theory. Thank you.
Thank you very much for the invitation, and I apologize for the misunderstanding of the time. And thank you so much for waiting for 1 hour. So I'd like to talk about 4D-2D duality, or the correspondence discovered by Beem, Lemos, Liendo, Piles, Rastli, Van Ries. So, as you know very well, they constructed a map from the category of 4D n equals to 2 superconformal field theories to the category of 2D chiral conformal field theories, which can be identified with the category of vertex operator algebras. And the feature of this map is you can compute the Schur index of 4D theory, which is an important invariant or observable of 4D theory as the character of the corresponding vertex operator algebra. So this is character. And this is nice because so Hilbert space here cannot be understood as a reducible representation of big algebra, but here Hilbert space is a reducible representation of a big algebra, which is nothing but this vertex operator algebra. So you can compute Schur index using a representation theory of the vertex operator algebra. And this map is defined as the dimensional reduction. So you might think this loses many information, but it turned out this map seems to be injective. At least it's true in examples so far. So there's a chance that this VOA VT is a complete invariant of this extremely rich theory. So it's important to understand corresponding vertex operator algebra. And another thing is that the image of this map is never unitary, which is unusual for physical theory. But this is because we have this relation where C2D is a conformal central charge for VOA, and C4D is a central charge for 4D theory. So if you start, because central charge takes positive value for unitary theory, so if you start with unitary theory, you end up with a non-unitary theory. So in particular, this map is not surjective. So it's natural to ask what kind of full subcategory the image of this map looks like. And there's this remarkable conjecture by Beem and Rastli, and which says the following. So for any 4D n equals to 2 superconformal field theory, the corresponding Higgs branch, which is a geometric invariant of 4D theory, it can be recovered from vertex operator algebra as the associated variety. And the associated variety of a vertex operator algebra is defined as follows. So this is very easy to define. So it's a spectrum of some Poisson algebra here, which I denoted by RV. So this is certain quotient of vertex operator algebra itself. And so vertex operator algebra can be thought as span of a normally ordered product of descendants of a generating field. So this is a generating field, and you consider a quotient of this space by a sheets V, which is spanned by elements of this form, which contains at least one derivative. So you model out all such elements, and then you find that this quotient space has a structure of Poisson algebra defined as follows. So the product is just a normally ordered product, and the Poisson bracket is just the first term of the OPE. And because this is a Poisson algebra, and the spectrum of this ring is a Poisson variety. So I have to remark that this is the associated variety is only a Poisson variety, but Higgs branch is a hyperkähler cone. So the vertex operator algebra coming from for this theory has a special feature that the associated variety is a hyperkähler cone. So let me explain example of associated varieties. So if G hat is a affine Kac-Moody algebra, you can consider corresponding universal affine vertex operator algebra, which is just a vertex operator algebra associated with this affine Kac-Moody algebra. But I don't model out by any null field. So there's no null field, it's just an induced module. And this vertex operator algebra is generated, of course, it's generated by fields corresponding to elements of Lie algebra with this standard OPEs. And the representation of this vertex operator algebra is nothing but the representation of G hat at level K. And if you remember the definition of associated variety, you find that this is nothing but the G star, because this VOA is generated by elements of G. And Poisson structure is given by this first term of the OP, which is nothing but the usual Poisson structure here. And because there's no null field, we don't model out by any relation, so it's just G star. But if you consider a simple quotient of VKA, VKG, so if you model by a relation coming from null fields, and so it becomes smaller. So it's a subvariety of G star, which is G invariant and conic. And it's known that if LKG is a vertex operator algebra associated with the Zumino-Witten model, which is integrable, then the associated variety is just a point. It's just a fat point. So any elements elements of positive conformal dimension in sheets algebra is nilpotent. And in fact, it's known that the converse is also true. So you can characterize integrability condition as the so this zero associated variety condition characterizes integrability condition. So in other words, you can generalize integrability condition to any vertex operator algebra by considering this zero associated variety condition. And this condition is called a least or Shitsuko-finite. So this is a very important condition which satisfy vertex operator algebra associated with rational conformal field theories. And it's known that this least VOA, so has very nice properties such as a finiteness of simple modules and modularity of characters and the existence of tensor categories and so on. But of course, in terms of Beem Rastri conjecture, this zero associated variety condition means that there's no Higgs branch. So we cannot impose this condition to study VOA is coming from 4D theory. And there's more.
Is this bigger than the set of chiral algebras you get from rational conformal field theories, or it's?
It's bigger because we don't impose semi-simplicity conditions here. So if we impose semi-simplicity condition, which is often called rationality condition, then it should be the same. But this contains so-called logarithmic VOAs. Okay, so this is a well-known case, but there's a less known case which corresponds to a representation called admissible representation. So this is a case when a shifted level is a positive rational number. So because this is if and only if so this because of this condition, this cannot be least, but one can show that the associated variety is a nilpotent orbit closure of some nilpotent orbit. And this is an example of a hyperkiller cone. And it's known that this is indeed come from 4D theory, more precisely some Douglas theory. If case not all admissible representation come from 4D theory, but if it's a boundary admissible, so this means that if you write K plus a check is P over Q, and if to be admissible, P has to be equal greater than the dual Coxeter number. The boundary means that this is smallest as possible. And if such a condition is satisfied, then it's known that this representation of Kac-Moody algebra comes from 4D theory. Okay, so as I said, we would like to study 4D theory coming from 4D theory. We would like to study a vertex operator algebra coming from 4D theory, but we cannot really impose this least condition, which usually assume in VOA theory. So we need to relax this condition. And one candidate for this condition is this quasi-least condition. So we call VOA quasi-leaf if this associated variety has a finite remaining symplectic leaves. And because it's a Poisson variety, you can consider symplectic leaves. And if leaves are finite, we call it a quasi-leaf. And the VOA coming from 4D expected to be quasi-least, if I understand correctly. And this is certainly a finiteness condition. And so So in the case of represent a VOA associated is affine Kac-Moody algebra, this is quasi-least if and only if this variety is contained in the nilpotent cone. So this simply lives in this is a quadjoint orbits, and quadjoint orbits, nilpotent quadjoint orbits are finitely many. So if this condition is satisfied, then it's certainly quasi-least, and you can show that the converse is also true. And so the admissible affine vertex algebra is quasi-least because it's a closure of a nilpotent cone. But this is not the only case. There's some discrete. There's some series outside. For example, if you take G from so-called Deligne exceptional series, which is a series A1, A2, G2, D4, E4, E6, E7, E8. And if you take this special value of a level, then you can compute the associated. In general, it's difficult to compute this associated variety, but you can actually compute this minimal associated variety and show that it's a minimal nilpotent oblique closure. So this one is quasi-least. And if G is A1, A2, G2, F4, then this is actually admissible representation. So this is nothing but this statement. But if G is D4, E6, E7, E8, then this is a negative integer. So some unusual level to consider. But this is in fact the first example of VOA coming from for the theory that appeared in their papers.
Remind us, varying the level, what do you change in the four-dimensional gauge theory?
There's a level for this theory. I forgot the relation, but the I don't know what.
Even roughly, like, are we changing couplings or we're?
I think so. Correct me if it's wrong. Is that okay?
So I think it actually depends very severely on the data of the four-dimensional theory, and it roughly corresponds to different ranks and yeah, I don't know the relation exactly, but I think it depends very severely on the data about the 4D theory, and K just is not continuous parameter. You shouldn't be thinking about it as a continuous parameter. It rather happens that at some special levels of K, you get something, you get characters that appear as sure indices of a four-dimensional theory. But the translation between the data of 4D theory and the 2D CFT doesn't seem to be anything like simple.
And what do you remember of the dictionary? Just remind us.
Maybe it might be actually easy to discuss one parameter family of examples. Tomoyuki, are you going to discuss, for example, these W algebras and their relation to the Argyll-Douglas theories? These.
It's not really one parameter family. It's a discrete.
Yeah, I know. Like discrete, but there's like an infinite set of examples, right? Labeled by one or two numbers, right? And
I think he mentioned that Argyll-Douglas theories. It was just a little too fast to translate. Maybe just review again.
So it just so for Argyll-Douglas theory correspond to exactly this boundary admissible levels. So roughly you can. So it depends on this denominator.
Right. So maybe there's these Archer-Douglas theories are labeled by two integral numbers, right? Or two. They're just labeling an, am, right? For example.
This so that's label correspond to G rather.
I'm just because Mina is asking about like, I guess some kind of example where you can really see how is the K and how is the G related to a particular four-dimensional theory, right?
Maybe it's better to explain this example. So this is the example which correspond to elliptic fibrations. And the surface, elliptic surface can be described by, as far as if I remember correctly, it can be described as orbifold of elliptic curve times P1, quotient by the action of G, action of cyclic group, which is nothing but this number.
And here I should I envision my 4D CFT as coming from some Calabi-Yau singularity?
No, not necessarily, I don't think. But this case, yes.
Our seminar is very informal, as you can see, so it also serves a purpose for us to learn.
Sorry, I couldn't hear.
Our seminar is extremely informal, so don't get it.
So I'm not physicist, so I'm not very. I'm sorry if I cannot answer your question properly.
So if somebody knows, maybe they can educate me.
Maybe Miroslav can answer this question. Shall we?
I've never really worked on like this correspondence very much, and I'm afraid that I'm unable to recall any enlightening examples at this point.
Okay, so maybe I should think about like Seiberg-Witten curves and some special points in the moduli space of Seiberg-Witten curves where we tune things and then I get a singularity. And the associated CFTs. Is that what I'm trying to do?
I don't think so.
Yeah, I don't think so either.
You're more looking at the Higgs branch of the theory.
Right now we're looking at Higgs branch. So also, good. So the relation to the Higgs branch, should I think of this as basically Higgs branch providing the free field formalism for the associated chiral algebra?
Yeah, I think so. Yeah, I remember seeing some. Yeah, so maybe Tomoyuki can comment on that.
Sorry, I couldn't catch your word.
Does this does Higgs branch provide some kind of information for a construction of free field realization of the algebras?
Right. Yeah, that is what is expected by Beem and rest. Yeah. Yes, that's correct.
In other words, these chiral algebras are related to theories in vortices in the four-dimensional gauge theory.
I think so.
Oh.
Sounds about right.
Shall I continue?
I apologize for this interruption. I just needed to worry.
Okay, so this is this is another example of VOAs that come from 4D theory. And so what can we say in general about this quasi-Lees VOAs? So first, one can show that there exists only finite many simple ordinary representations. Ordinary representation means a representation which whose character makes sense. And so this ordinary representation satisfies converges to a character of this ordinary representation converges to a holomorphic function on the upper half plane. This is plane, and this satisfies one linear differential equation called the modular linear differential equation. So the point here is that this solution of this modular linear differential equation is invariant under the natural action of a modular group SL2G. So this states certain modularity property of the characters, although I don't claim that this character span this solution. So this means that if you believe in Beem Rusty conjecture, then and if you believe that the VOA coming from 4D are quasi-Lees, this means that the Schur index, so the Schur index should be a character of the VOA itself, so it satisfies this modular linear differential equation. So it gives a modularity of the Schur index, so which I believe important in physics. Okay, so I said, so this Beem Rusty conjecture is not really a mathematical conjecture because it states something about 4D theory which is not really defined mathematically. So you have to to make it mathematical sentence, you need to define Higgs branch, for example, differently. And this is done. This is doable for the so-called theory of classes. So this, as you know very well, this stands for 6. So it's a 4D theory which obtained from a 6-dimensional theory by compacting fine on a punctured Riemann surface. So it has this Riemann surface as a parameter, and as well as this flavor symmetry group G, which are a complex semi-simple group. And for this class of 4D theory, Moore and Tachikawa gave a mathematical description of the Higgs branches in terms of 2D TQFT up to a conjecture. But fortunately, a conjecture has been proved by Braverman-Finkelberg-Nakajima. So we now have a very nice mathematical description of Higgs branches of a classes theory. And so one of the statement of Moore and Tachikawa is that it's sufficient to describe Higgs branches for genus 0, a Riemann surface, that you can glue them to obtain Higgs branches for higher genus. So let me recall Braverman-Finkelberg-Nakajima description of a definition of a Higgs branch for classes theory for genus 0 cases. So the construction goes as follows. So this MTR, this should be a Higgs branch for P1 with R punctures. And so this is defined as follows. So so it's a bit complicated. So you need to consider a Lagrange dual of G, and then you consider a corresponding affine Grassmannian. Then you have a
oh, here. Relative to the original problem, who is our G? The big G.
big G is a flavor symmetry group. And you take a dual. And then, so you have a geometric Satake, which says the equivalence of Pabas sheaves on affine Grassmannian with a representation of G. And you have a regular representation here, and you have a corresponding a sheaf, which is denoted by AR. And you consider a box tensor product of this sheaf on this product of affine Grassmannian, and you pull back to affine Grassmannian to get some sheaf on here. And then when they show that this is a ring object, so that this ring has a structure of a commutative algebra. So you can take a spectrum to get some algebraic variety. And the statement is, so this is very fancy way to define finite dimension of variety. But this is a right object. And this MTR, so this is already non-trivial statement. MTR is a possibly singular symplectic variety with a Hamiltonian action of R copy of G check. And there are some initial condition, MT2. So this one should have two commuting action of sorry, this should be G, not G check. This has a commuting action of G, two commuting action of G, and so this one is the simplest example of such a symplectic variety, which is a cotangent bounded to G. So this has a right action, left action of G. So this has two commuting action of G, and this is certainly symplectic. And MT1 is a product of G and so-called constant Slodrich slice that appears.
I'm sorry, another really stupid question. R here is what?
R is a number of punctures of a Riemann.
On genus zero surface.
Yes, exactly. So this is known to be a symplectic variety. And yes, and the last condition is this associativity condition. So the statement is that so there's R action of G here and S action of G here. You pick one action from here, you pick one action from here, and you consider a symplectic reduction with respect to the diagonal action of G. And the statement is that this is well defined and isomorphic to a Moa-Tachikawa variety for R plus S minus 2. So the Moa-Tachikawa conjecture was the existence of a symplectic variety satisfying this condition. And BFN proves their conjecture by constructing using symplectic variety using this fancy technology. And as you cannot hear.
What's S relative to the R is the number of punctures, and what's S?
This is also number of functions.
Also, and why is it not sufficient to work with a sphere with 3 punctures? Why do we need to consider?
Yes, you are right. It is sufficient to consider MT3, because we know MT1, MT2, and if you look at this formula, if you know MT3, you know everything. You're completely right. And yes, so by more Tachikawa, this MTR is exactly the Higgs branches for the P1 with R punctures. So maybe I should explain to relation to Coulomb branches of 3D theory. And so if you given a 4D theory, you can do S1 compactification to get the 3D theory. And if I understand correctly, the Higgs branch remains the same. But if you go to a 3D theory, you can use the 3D mirror symmetry to identify Higgs branch with Coulomb branches of the mirror theory. So this Higgs branch can be identified with a Coulomb branch of some 3D theory. And for type A, this is known to be a 3D gauge theory associated with a star-shaped with R legs. So this Higgs branch is nothing but the Coulomb branch of these 3D theories. And this is why we study this the Higgs branches.
Can I ask a question? It's not necessarily a question just to you, but it's also true that the Higgs spread doesn't change if you go, well, if you want to say if you go up a dimension. Now, we wrote down, I think some years ago with Nathan and others, actually a deformation of these theories that you can think about them as replacing the 4-dimensional theory by a 5-dimensional theory on a circle, where writing down what the theory is completely explicit, like it's a quiver gauge theory. And for that quiver gauge theory, the Higgs branch is just a quiver variety. And it's been done for like, I think all 80 types. So I wonder whether this has been compared to what these guys did. And if it hasn't, somebody should.
I don't think so. But do you but maybe I'm wrong. It's a very interesting remark. I should have a look. Okay, so yeah, so anyway, so yeah, so what one, so it's in general conjecture that this Higgs branch has finitely many symplectic leaves, but it's been proved for Coulomb branches by Weeks recently. So at least for type A, we know that this has finitely many symplectic leaves. So yes. Now we want to discuss what are the corresponding VOAs. So these VOA are called chiral algebras of classes. And so the conjecture that the chiral algebra of classes should have the similar description as a Higgs branch in terms of 2D TQFT. So you should be able to upgrade BFN construction to the setting of a vertex operator algebra. So what we want to do is the following. So you want to replace G flavor symmetry group to the corresponding affine Kac-Moody algebra. So G is of course a D algebra for G. And so we want to replace symplectic variety. So this is the more Tachikawa varieties to a vertex operator algebra whose associated variety is the symplectic variety. And so there's also, we also need moment map because this associativity condition is described in terms of a symplectic reduction. To do symplectic reduction, we need moment map. And moment map is replaced by a vertex algebra homomorphism from affine Kac-Moody algebra to V, because if we take associative variety of each, it induces a morphism from variety for V to variety for VKG, which is a G star. So this should be coincides with a moment map. And so this symplectic reduction should be replaced by a symplectic reduction for vertex operator algebra, which is described as a relative semi-infinite cohomology or the coset construction. And so this is, so because if you take associated variety of this vertex operator algebra, you recover this symplectic reduction in nice cases. So this should be the right thing to do, except that there's one constraint. To make this, to make this sense, the level must be minus 2 times h. So this means level here must be, level of each must be minus h, which is critical level. So we have to work everything over a critical level. And the Moore-Tachika variety for R equals 2 for 2 punctures was a cotangent bound to G. And so we want to replace this so if you follow this recipe, you want to avoid whose associated variety is a cotangent bound to G, but there's a natural candidate. So quantization of cotangent bundle is a differential operators on G, and there's natural affinization, which is called a CDO, chiral differential operators. And of course, we work over on the critical level. So this one is equipped with 2 commuting action of affine Kac-Moody algebra, corresponding to right action and left action at the critical level. And you do recover a cotangent bound to G by taking associative variety. And MT1 was a product of G and Constance-Rodois race. This one is obtained from cotangent bound to G by so-called constant reduction. And affinization of constant reduction is Dunning-Sokolov reduction. So this means we should replace MT1 to Dunning-Sokolov reduction of CDO, and then you do recover this variety by taking associated variety. Okay, now I can state the statement. The statement is that for each semi-simple group, there exists a unique family of vertex operator algebra, such that the analog of Moore-Tachika variety holds. So one was the, so there exists a vertex operator homomorphism from tensor product of R tensor product of affine vertex algebra at critical level. So this corresponds to R commuting action on the Moore-Tachika variety, and there are some conditions. And also V2 is a CDO, so this corresponds to MT2. And V1 should correspond to MT1, so it's a Dunning-Sokolov reduction of a CDO. And this associativity condition, so analog for the associativity condition. So R plus S minus 2 is a reduction of R tensor S. And so there exists a unique family satisfying this condition. And in fact, you can show that each VR is simple and conformal. So it has a stretched energy tensor. And the central charge is described in terms of dimension of a Moatachika variety. So minus 20, something like this. And there is an explicit character formula for this VR. So this one is just induced module. So this is very explicit. And there's some factor here. And finally, associated variety of each VR is isomorphic to Moatachika variety for R punctures. So this is a statement, and so this conditions, this 1, 2, 3, and this, sorry, this and this. These are a condition that chiral algebra of classes should satisfy, according to this paper. And because of the uniqueness statement, this means that the VR should be the chiral algebra correspond to P1 with R punctures. And the last statement means that the Beem rastery conjecture is true for classes theory.
No, your character just factored, right? So they were just a product of R characters of something simpler.
So this is a product of R characters, but there's this factor. So it's not exactly the product.
Okay. I mean, I would have thought that there, could there be another algebra where basically you get a single algebra for many R's, you just ask about different characters. For example, for which this would be just a character of some tensor product representation.
You're asking whether it has a Hop algebra-like structure?
Yeah, I mean, for example, if we, I mean, wouldn't it just, maybe I'm confusing something. Okay. Yeah, I suppose so.
Yeah, as you said, I think it's important to consider this family at the same time, but I don't know whether you can view as a single family. Yes, so
actually, maybe I should ask a different question. So, by Kyoto's conjecture or construction from 2012, you would also associate to the same theory some double algebra where with punctures you would consider you'd get some correlation functions of the double algebra itself. Is there a relation between this conformal field theory question you're asking and the one Davide was asking? It doesn't obviously have to be one, but because suddenly we're asking about a Shor index and not the kind of question Davide was asking.
I don't think I know that work of David. How can you explain more how they associate double algebras?
So to the same four-dimensional theory, now we are associating two different a priori chiral algebras, right? So Davida's statement would be that if you were to study some partition function of a 4-dimensional n equals 2 theory on roughly on R4, that
Are you talking about AGT?
Yeah, I mean that's all I'm saying, right?
I don't think there's a direct connection. It's somehow the same spirit as AGT, but I don't think there's a direct connection.
Yeah, it does not have to be direct, but we're studying the same physical system which is constrained by the same set of symmetries, and we're not doing anything that drastically different to it.
But we are looking from on the same system from slightly different perspective, right? If you look at the like Davida's story, you have two omega backgrounds along the two C2s, and then you have the class S Riemann surface. The chiral algebra that Tomoyuki is talking about live on a plane when you turn off one of these omega backgrounds, right? On the other hand, the Davides VOA lives on the class S curve. So to relate these two, I think you would have to turn off one of the omega background parameters in Davides context, and then compare the two chiral algebras that you get on either of the two Riemann surfaces, either the C2 that you can potentially make into something more complicated, and the C2 that comes into the game from the class S construction.
But turning off one of the omegas is not that unnatural, right? It's some kind of beta to infinity. It's some classical limit of the double algebra.
Yeah, I guess what I'm just saying that in order to
it's not direct. That's I agree.
To do, but it doesn't seem to be like very direct.
It's not completely direct. I agree.
Yeah, it'd be very interesting to find exact connection, but I don't know. Yeah, so this statement is done by constructing this VR explicitly. So this means you can compute this chiral algebra of classes in principle, although it's very hard computation. And maybe so I'd like to explain some examples. So the easiest example is of course the case of SL2, and so MT3 is essential one, and this one is quite simple. We just a tensor product of 3 copy of C2, and this should have 3 commuting axiom SL2. And so each one has a natural action of SL2, so which induces the 3 commuting action of C2, and the symplectic structure here induces the symplectic structure here. And the corresponding VOA is a natural affinization of the quantization of this symplectic vector space. So quantization of symplectic vector space is a wide algebra. And affinization is just a beta gamma system. So V3 is just a beta gamma system associated with this symplectic vector space. So this is free field, so this is very easy. But if you consider MT4, what you get is the minimal nilpotent of closure in D4. This one should have a 4 commuting action of SL2, but this can be seen if you write a affine dinking diagram for D4, and you find the 4 commuting action of SL2 here. So the non-triviality here is that somehow D4 appears, although we are considering SL2, and this variety is singular.
Could you say again what do you mean by okay? What do you mean by beta gamma system associated to the symplectic vector space? Just spell it out. What does that mean? For somebody who just knows beta gamma systems.
So this is eight-dimensional. So if you have you take a basis 1, 2, and so there's a form here, symplectic form. So you consider field satisfying these conditions. So this is exactly a beta gamma system, I think.
I see. Thank you.
And yeah, so this is quite non-trivial. Yeah. So and then corresponding VOA is affine, simple affine vertex algebra for D4, and at level -2. And -2 is, of course, a critical level for SL2. And so this means that the associated variety of this one is isomorphic to this minimal nilpotent orbit closure. But this already I explained. So this reproves the previous result of myself and Moro. And associativity implies that this product symplectic reduction of this symplectic vector space is isomorphic to a nilpotent orbit closure in D4. So this is already non-trivial statement for me. This is well known as ADHM construction of the minimal nilpotent orbit closure. And for VOA, this statement becomes this. So affine vertex algebra for D4 at level -2 can be obtained from a beta gamma system by doing a coset construction. So in general, this associativity condition gives a family of very non-trivial isomorphism between symplectic varieties and the vertex operate algebras. And also this representation, the character is, in general, we know that the character of affine Kac-Moody algebra representation can be expressed in terms of a Gaussian-heuristic polynomial. But so for this case, this polynomial is very non-trivial, so you don't really expect that it has a simple formula. But if you apply this modular linear differential equation, you find that the character can be explicitly expressed as this. This is a very simple formula, which is a bit surprising. So this is another. So of course we have a general formula of the character, which is compatible with a non-Schur index formula, but this gives another formula for the character, for the Schur index.
Maybe I should have asked a different question. Rather, this is definitely the question I should have asked. When these relations are conjectured, does it proceed by, do people have a conceptual understanding which chiral algebra you will get? Or you compute a Schur index and then you try to read off the character from it and then build a story how you operate with the characters? Or is it known, sort of, do you have a physics derivation of which chiral algebra you're getting? One should be getting from.
I think in general, people guess VOA from Higgs branch. If you know Higgs branch, you can guess what it is. If you believe in Beem silicon, which I think accepted. Okay. Yeah.
Okay.
And for SL3, so the more attached MT3 is a minimal nilpotent orbit closure in E6. And again, you find 3 commuting action for SL2 here. And again, VOA is affine vertex algebra for E6 at level -3, and -3 is a critical level for SL3. But you cannot continue forever like this because you go outside of the linking diagram. And in general, neither this one and this one has a simple description. So in general, this chiral algebra of classes is a double algebra in the sense that it's not generated by Lie algebras. Okay, maybe if you don't have any question, I'd like to make some words for the proof. So I just want to give you an idea of the proof, which is not so difficult. So V2 should satisfy if the associativity condition means that this condition. So this doing this operation doesn't change VR. And you may ask why it should be true, but there's a very natural explanation for this. So by definition, I didn't define CDO, but it's very easy to define. And from this definition, you find that the module of the CDO is nothing but the module of the D module on the loop group. Or strictly speaking, it's critically twisted D module on the loop group, if you properly make sense of this category. So this means that if you consider a D module of the affine Grassmannian, which is a quotient of GT by GT, so this one affine Grassmannian is a quotient of this one by this. So this category is equivalent to the category of a GT equivariant. So this equivalence restrict to this equivalence. So this one is the category of a GT equivalent module of a CDO. And through this correspondence sense, the CDO itself corresponds to the delta function D module here at identity. And you can further restrict this equivalence to the GT equivalent D module on the affine Grassmannian. So it should be, it restricts to the equivalence to the category which are equivalent to both action of GT. So there's a left and right action of G hat. And when geometric Satake implies that this isomorphic to the category of a G-check, a representation of a G-check. But this is not just the equivalence of abelian categories, but it's an equivalence of tensor categories. So you have a tensor product here, you have a convolution here. So you have some operation which correspond to convolution on the affine Grassmannian. And this is nothing but just this coset construction according to Frankel category. And because CDO correspond to a delta function at identity, and which correspond to C. So, and tensoring with C doesn't change anything. So it means that we have this condition for any object coming from, belong to here. But in fact, this isomorphism holds for more general G hat module. So this isomorphism holds in general. So you conclude that this should satisfy the associativity condition for V2. Yeah. So this coset construction correspond to convolution on the affine Grassmannian. And so V1 is a Dirichlet-Sokolov reduction of CDO, and associativity condition means that this decreases punctures by 1, and you can show that this is nothing but the Dirichlet-Sokolov reduction of M. So this means that the VR minus 1 is a Dirichlet-Sokolov reduction of VR. So you can, so this means that because we are given V1 and V2, you can, if you can invert this reduction, you are done. So it's enough to construct to an inverse functor to Dirichlet-Sokolov reduction. Or if such a construction is possible, you should be able to recover everything from a V1. So what you want to do is you want to try to recover everything from V1. And if such a construction is possible, you should be able to recover, for example, V2 at least from V1. So now the question is whether we can reconstruct V1 from V2 from V1. So the V2 has 2 commuting action of jihad, and this has only 1 action. And so very easy guess is just consider tensor product of these 2, but this is too easy, it doesn't work. But the reason is the following. So that there's 2 actions of jihad here, but there are relations. And the relation is that the Feigin-Frenkel center acts, the action of a Feigin-Frenkel center for the right and left are the same. So, and this is the only relation. So you have to identify 2 actions of a Feigin-Frenkel center. And there's a very natural way to identify. So you can kill the difference of 2 actions by considering a certain BRST operator, BRST cohomology. So Feigin-Frenkel center is a commutative vertex subalgebra generated by V1 to rank R field. So in the case of SL2, there's only 1 field which corresponds to renormalized Sugawara vector. And if you consider BRST operator which kills a difference of successful action, ith action and I+1 action of this element, and this operator is nilpotent because these are commutative. You can kill the difference of a Feigin-Frenkel center. And so remarkably, this construction works very well, and you can check this satisfy the conditions I explained in the statement. So this is a rough idea how you prove the theorem, and this gives you a construction of the chiral algebra classes. Okay, so maybe I explained everything I wanted to explain.
Okay, thank you very much. Are there any questions?
Maybe I have a brief question.
Yes.
So when you, the results you give, they're all for pure Higgs branches, right? I mean, you're never discussing mixed Coulomb Higgs branches in this work, correct? In this talk.
Yeah.
Is there anything known about these branches? Because I mean, they certainly exist, right? But you'd expect probably the structure to be more complicated.
Yes, I'm not aware. Does anyone knows?
I mean, well, they're mixed branches, they're factor, right? You think you're gonna get something interesting? This is gonna be a product of something smaller. Mixed, I mean, Coulomb times Higgs, so.
Yeah. So this now this VOA relation with VOA and Higgs branch is now clear, but relation to Coulomb branch is not yet clear. It's expected. There are some relations, for example. It's known that the yeah. So many things to do for Coulomb branches, I think. Sorry, I cannot hear you.
When you prove your statements, the geometric connection to the Higgs branches, do you use it implicitly somewhere, or the proofs are different from? Does physics help in proving these things?
You mean so?
For example, the relation to Drinfeld-Sokolov and this kind of recursive thing you have.
So sorry. So of course, I'm not sure I understood your question correctly, but of course I didn't consider this problem without the physical motivation, and yeah, I never thought of this kind of problem, and yeah, I just proved conjecture of Beem all. So this is not my idea. Is that what you?
I mean, for example, Miroslav Davide, you guys used Drinfeld-Sokolov reduction in many cases to actually construct that in a different context, right? Chiral algebras associated to that come out of string theory in some ways. Does this application resonate to you? Can you, Miroslav, translate what's?
Here they are doing something very differently looking. Yeah, so you're basically, so in our case, there was a good reason why Drinfeld-Sokolov reduction should play any role, because it was just imposing some boundary condition, some physical setup, and whatever. On the other hand, here, why things like Drinfeld-Sokolov reduction should be expected is not clear to me. Yeah, I don't think I have anything sensible to say.
So Drinfeld-Sokolov reduction is a way to construct the quasi-Lis VOA from quasi-Lis VOA. It preserves quasi-Lis property. So for me, it's natural that the Drinfeld-Sokolov reduction appear.
So maybe I have a question, Tomoyuki. Is the presence of the BRST reduction or in the construction of the VOA somehow related to the Higgs branch having a description in terms of a symplectic reduction?
What is your question?
Yeah, sorry, I don't know how to ask.
One can certainly relate changing the number of punctures to changing some kind of boundary conditions. That's in some sense there in the setup of class S. we're getting a little bit like, the story of integrability. It pops up in so many places, and wherever you turn is there. So wherever you turn, there are chiral symmetries. It would be somehow nice to have some kind of unified world where they all live. And we don't have a zoo of different animals, or rather one zoo for all animals, not several zoos for what should have been the same animals. Do we have more questions?
Well, if not, then thank you, Tomoyuki, again. Thanks everyone else for joining, and see you not the next week, but the week after, because there's, I think, Columbus Day next week.
Thank you for joining us, for agreeing to come so early. And, I really enjoyed your talking, that you made me think.
Thank you very much.
Thank you.
Bye-bye.
Bye.